Hi, dear colleagues. Today, I am here with a new study about next-generation nuclear energy technologies that will transform our future and reshape the global energy landscape. The world's energy system is being pushed to its limits. Rising demand, unstable grids, and global decarbonization targets have created a critical need for clean, reliable, and secure power. Two technologies are emerging as game-changers: small modular reactors and nuclear batteries. SMRs represent the next generation of nuclear design. Built in factories and shipped to site, they use passive safety systems, modular construction, and advanced fuel cycles to provide flexible, low-carbon electricity. Their output, typically 50 to 300 megawatts, makes them ideal for distributed power systems, industrial heat, hydrogen production, and replacing fossil fuels. With near-zero emissions and over 90% capacity factor, SMRs strengthen energy security while supporting the clean energy transition. Parallel to SMRs, nuclear batteries are redefining long-duration power. Using radioisotope decay and either thermoelectric or photovoltaic conversion, these systems can operate continuously for 10 to 50 years with no maintenance. They deliver stable energy in extreme environments, from deep-sea sensors to satellites and defense installations. They power critical infrastructure, medical devices, autonomous drones, communication nodes, and scientific missions where ordinary batteries simply cannot survive. Together, SMRs and nuclear batteries represent a new era of energy: clean, reliable, and resilient. As nations push for energy security and low-carbon solutions, these technologies will play a leading role in shaping the future. The future of energy is changing. Are you ready? Let's dive deep into this important topic together. Dear colleagues, today, the global energy landscape is experiencing one of the most significant transitions in its history. Electricity demand continues to rise, climate change pressures intensify, and the need for secure and diversified power sources is now tightly linked to national security and economic stability. In today's article, we're going to dive into the strategic role of small modular reactors and nuclear battery technologies in the future of global energy. In this complex environment, one conclusion becomes increasingly clear. A sustainable and reliable energy future is not achievable without nuclear energy. And within the nuclear field, two technologies stand out as foundational pillars for the decades ahead: small modular reactors, known as SMRs, and advanced nuclear battery systems. This video essay examines the scientific, technical, and strategic importance of these technologies, and explains why they are rapidly becoming central to 21st century energy architecture. Alright, let's dive deep into this important topic together. First, the growing importance of nuclear energy. Nuclear energy remains unique among all large-scale power generation technologies. It delivers consistently low life-cycle carbon emissions, very high capacity factors, often above 90% weather-independent, stable baseload power, operational lifetimes that can exceed 60 years. These attributes make nuclear energy an essential component of any long-term decarbonization strategy. As countries seek to reduce greenhouse gas emissions while ensuring stable and affordable electricity, nuclear power offers a combination of reliability and sustainability that few other technologies can match. Second, small modular reactors, next-generation nuclear systems. What SMRs are? Small modular reactors are advanced nuclear fission systems with capacities typically below 300 megawatts electric per module. Their defining feature is modularity. SMRs can be manufactured in factory environments, transported to the project site, and assembled much faster than traditional large reactors. Safety characteristics. SMRs incorporate passive safety systems that rely on natural physical processes, such as gravity, convection, or natural circulation, to provide cooling. This means the reactor can safely shut down or stabilize without external power, pumps, or human intervention. Such features significantly reduce operational risk and enhance overall system stability. Operational flexibility and economic benefits. SMRs deliver shorter construction timelines, lower upfront capital investment, scalable deployment. Units can be added as demand increases, compatibility with hybrid energy systems, high resilience in regions with extreme climatic variability. Additionally, SMRs require less land and can operate in areas where traditional large-scale plants are impractical. Strategic impact on energy security. SMRs improve energy security by reducing dependence on imported fossil fuels and by diversifying the national energy portfolio. Their long fuel cycles, often 18 to 24 months or more, increase resilience against supply disruptions, making them highly valuable for countries without abundant energy resources. Fourth, the expanding frontier of nuclear battery technologies. Parallel to advancements in reactor design, nuclear battery technologies are undergoing rapid development. Also known as radioisotope power systems or photovoltaic batteries, these technologies convert the natural decay energy of radioisotopes into electricity. Technical advantages. Nuclear batteries provide extremely high energy density, operating lifetimes measured in decades, resistance to extreme environmental conditions, very low maintenance or complete maintenance-free operation. Their predictable and stable output makes them ideal for mission-critical applications. Industrial applications. In industrial and infrastructure monitoring systems, nuclear batteries offer uninterrupted long-term power for remote oil and gas instrumentation, mining sensors, deep-sea equipment, long-distance pipeline monitoring, autonomous environmental sensors. These environments often lack reliable access to conventional energy or regular maintenance. Scientific and space applications. In space science, nuclear batteries are indispensable. Every deep space mission, from Voyager to Cassini, from Curiosity to Perseverance, has relied on radioisotope power systems. Solar power becomes ineffective in deep space, and only nuclear batteries can provide the long-duration, stable energy required for decades-long missions. National security and defense. Nuclear batteries support long-endurance surveillance platforms, autonomous defense systems, strategic communication hardware, remote border security sensors. Their longevity significantly reduces logistical vulnerability during prolonged operations. Medical and healthcare uses. In healthcare, photovoltaic nuclear batteries can power pacemakers and long-life implants, emergency medical devices, portable diagnostic systems. Reliability is crucial in these applications, and nuclear batteries provide unmatched continuity. Fourth, a combined strategic perspective. Small modular reactors and nuclear battery technologies do not compete with each other. They complement one another across different scales of energy need. SMRs provide grid-level, continuous, decarbonized electricity. Nuclear batteries deliver micro-scale, autonomous, long-duration power for critical systems. Together, they offer a comprehensive nuclear-based energy architecture capable of supporting national energy security, industrial modernization, advanced scientific missions, digital infrastructure, long-term decarbonization. This dual advancement strengthens technological sovereignty and supports both civilian and strategic objectives. As a conclusion, we can say that as the world accelerates toward cleaner and more resilient energy systems, nuclear technologies remain indispensable. Small modular reactors, with their modular manufacturing, enhanced safety, and operational flexibility, represent the next major step in sustainable large-scale power generation. At the same time, nuclear battery technologies are enabling continuous, maintenance-free energy solutions across industries, national security, scientific exploration, and healthcare. Together, these innovations shape a future in which energy reliability, carbon reduction, and technological independence can be achieved simultaneously. In this evolving global landscape, the strategic adoption of nuclear energy, through both SMRs and advanced nuclear batteries, will be one of the defining factors in building a stable, resilient, and sustainable energy future. Thanks for watching. If you want more deep dive content on nuclear engineering, SMRs, energy technologies, artificial intelligence industry and the future of global power systems, don't forget to the motto. You have the power to build your digital future and shape AI for a more comfortable life and prosperity. Everything is always impossible until someone does it. Because everything is always impossible until someone does it. Stay connected, stay inspired. Take care until we meet again. Thank you.